I introduce Dr. Enis Karakhan from Connected Device to do the presentation for us. Please.
Thank you, Mohammed, for the introduction. We are very excited today to demonstrate a 3-year-long R&D that we collaborated with the Federal Highway Administration. So this is a SBIR Phase 2 project. It was funded under the U.S. Department of Transportation WOLP SBIR program. We have completed Phase 1 and Phase 2 projects. Now we are in the process to commercialize our technology. Today, I'll do a very brief introduction of our team and our company, and simply go over what we have done, our journey in this project. After the brief presentation, we're going to start demonstrating the technology. We'll simply showcase different outcomes of our R&D work. We have done quite a bit research, quite a bit product development, and a lot of engineering work in this project. So I'm really excited to share those results with you. If you can give me a second, I will start the presentation. So my name is Enes Karaslan. I'm the Chief Executive Officer at Connected Device. The sharing should be online. It's not connecting.
Looks like it's crashing like Zoom and
okay. All right, now it should. All right, perfect. So the presentation outline will be, I'll briefly go over our team members.
you need to share your screen on the Zoom because it's not showing you Zoom. Okay.
So I'll introduce our team first, and maybe talk about a little bit the motivation behind this project. And I'll go over what we have done in the Phase 1 and Phase 2 feasibility research and R&D. I'll talk about a little bit of the pilot projects we have done, and simply describe what we are going to demonstrate after the presentation, toward the end of the project presentation. So we are a very young startup based in Florida. We now have a team of 15 people. And our team is very experienced in machine learning research, intelligent transportation technologies. So I'll go over some of the key personnel who actually worked in this project. Dr. Tolga Ercan is also one of the key people in this project. He is very experienced in ITS systems, transportation safety, and connected infrastructure. He has completed his PhD research on these topics. Dr. Halukulaman is also one of the co-founders, and he has done quite a bit work in transportation safety, connected infrastructure. Mahta Zakaria, she is also here today helping us with the outdoor demo. She is doing her PhD research in computer vision, machine learning on these subjects. We are collaborating with the University of South Florida Center for Urban Transportation Research team. Vito from USF is also helping us today in the outdoor demo. So this is the motivation behind this idea. As we are all aware, connected automated vehicles are essential to our transportation. With just single intersection application, we can save more than 1,000 lives. And if we can deploy this technology to widespread level, now this is going to help us save $180 billion per year, just from the traffic congestion time. One of the biggest challenges in this connected automated vehicle is this communication infrastructure, namely infrastructure to vehicle, can be sometimes challenging to deploy. A lot of the times there's no power or fiber optic lines on the roads. And if it's a rural area, then these areas are very dispersed areas, and it may not be economically viable to provide the same standard of coverage. And in maintaining these wireless infrastructures, we use roadside units to send these wireless communication messages to the connected vehicles. This infrastructure can be, the maintenance can be very difficult sometimes and also expensive. There are a lot of challenges from electromagnetic interference to just incompatibility of the message formats. So we decided to come up with this idea of using smart traffic signs. They look like colorful QR codes here, but they are fundamentally different. We solved a lot of the problems coming from the challenging roadway environment. You have sometimes a rainstorm or a snowy day. Here in this technology, we communicate with the vehicles using machine vision instead of using a wireless communication channel. So that allows us to deploy these signs easily in rural locations where we don't have to bring power or fiber optic line. And the maintaining can be a lot cheaper compared to the wireless infrastructure. So this is a very brief description. When the vehicle recognizes one of the smart signs, it will activate the associated message by calculating the relative distance and heading and position in reference to a known road geometry data. These signs can solve a lot of problems. It can help also autonomous vehicles to localize themselves. But here in this example, there's a suboptimal road condition. The sign simply helping the vehicle to learn the road geometry information. And the vehicle now knows where the road damage is located in the upcoming road segment. Since the vehicle was able to localize itself, now all the vulnerable road users can be tracked to much higher accuracy in reference to this known road geometry data. We also wanted to make a small, affordable device for an aftermarket device that can help legacy vehicles also benefit from this communication technology. There are billions of vehicles on the market that is not equipped with any sort of machine vision system. So we were able to do this incredible device. It costs under $500, and it is able to provide a lot of advanced safety driver features from forward collision warning to lane departure warning, traffic sign recognition. But the unique thing here is it can recognize these signs and implement a lot of different infrastructure to vehicle applications. We designed a lot of different safety scenarios. We'll be demonstrating today several of them. And we also made a nice graphical interface that will minimize the driver distraction. So we are not going to show the driver a camera view or anything. So in the phase, in the phase one project, the idea was to use these unique image features. If we were to use unique image features instead of using a QR code or a barcode system, then we can actually solve this problem very robustly. We can match the message with the sign identifier so easily and tackle a lot of the challenges on the roadway. Our device is able to, we done in the phase one project a lot of machine learning work. The goal was to simply integrate an object detection system that could simply calculate determine the locations and the type of the road objects, and as well as calculate their relative distance to our camera. Since the goal was to make it really affordable, we done a lot of work in optimizing these models and trying to find the best optimal model that can be deployed in a small, affordable device. In the phase one, we've done a lot of proof of concept experimental setups. We tested the system under fog, cloudy, nighttime, under different varying speeds. We even tested under occlusion, where a tree branch covering the sign, or in a sunny day, sun exposure that is affecting the performance. It never snows in Florida, so we came to DC to be able to conduct the snow test. But the result was very promising in the phase one. We decided to follow this approach. We were able to prove the technical feasibility. So these are some. I can show this maybe later if you have time. To be able to create these messages, we also wanted to create an online tool that will make it so easy. You prepare your message if you can even use a US DOT's message creator tool. It is very easy to use. And after you create the message, you upload the message to our online web-based tool, and it will generate you a signed message and a graphic for the agency to be able to print this sign.
Are your signs dynamic or static?
So those are static, but we can actually implement a lot of dynamic information because we don't actually embed the message itself on the sign. We only use image features to match the message ID. So this allows us to update the messages. In the demonstration, we are actually doing some dynamic message update where we have a work zone simulated. We are changing the work zone configuration. And as soon as the vehicle enters a range of roadside unit, maybe located in a central intersection, the system will pull all the message updates in the vicinity. So we are going to do a couple loops. So every time a different message will be implemented for a different roadway condition, a work zone configuration.
So it's a fixed sign, but your interpretation may change based on your geolocation.
Exactly.
In this region, this sign means X. Within a different location, the same sign means Y.
Exactly.
Right.
We could also maybe use multiple signs, even determining the message content, different dynamic situations, maybe in the daytime, lane 1 is open open or lane 2 is closed at nighttime. So we can define also timestamps for this dynamic information. One of the main challenges in this idea was actually MUTCD itself. So MUTCD defines very specific shapes and colors and mandates those rules for local agencies to put these signs. Even though we did our best to change the design of our signs to at least match the color scheme in the MUTCD, it would still create some concerns for the transportation agencies to use these signs. They don't mean anything to the driver, so there's a little ambiguity. So it's not for the driver, it's for the machine vision, but the MUTCD is actually referencing only for driver considerations. So there is this unique problem. So we decided to do in the phase 2 some additional research, preliminary research, to investigate possibility of making the signs invisible to the human driver, but still visible to the machine vision system. The goal was, of course, still to make it as affordable as possible. So we decided to use a UV camera that can be easily converted from a normal camera. We simply use a special filter lens that will filter out all the visible light, but only take in the UV light to the camera. So here we simply put these thin film on the existing sign. You won't see anything if the thin film is good quality. It's not, if there's no glare, but the machine vision will be able to show a different shape on this sign, but the driver will not see anything. So here, as you can see, so in the UV camera, there's this unique shape on the merge sign, but in the actual scenario, there's nothing. We are going to be demonstrating today, even though it is cloudy, it will still work. We've done testing a couple of times today. We put the stop sign, and the stop sign is completely looks normal, but our unique camera will be able to pick up the message.
So, question. So the device incorporates this one as well, the original device.
Yes. So we simply hook up a external UV camera, since the preliminary research still in the phase 2 that we incorporated. We'll need more R&D work to be able to make it ready for commercialization. But what we are doing, one of the biggest challenges, for example, the car windshields are actually blocking the UV light. So it's not taking the UV light in. So our device, if we were to put a UV camera in our device, then it wouldn't see anything. But yeah, so we decided to make an external sensor, put outside the vehicle. It can still talk to the device inside the vehicle. So that's our solution. For these applications, it's always better to put the sensors outside anyways. Nighttime is also another challenge. As you all know, the main source of UV light is actually sunlight. So at nighttime, there's no UV light. So we decided to test if an external UV flashlight or external LED UV light will be enough to capture this image. So we got very good results during our preliminary experiments. So we put a small block of shape UV thin film here. It looks completely black in the camera, but other regions are reflecting the UV light. One of the good things about this is the current signs have the reflective property that allows us to get this UV light back to our camera. So the goal is to do use only off-the-shelf thin film material without needing to create something unique in thin film. We should be able to solve this problem. So I'm going to show these. Okay. We done a lot of demonstrations and testing, but one of the main goals in this project was to create a complete platform environment for automated vehicles. So if there is an automated vehicle that is already equipped with necessary hardware and sensors, then we wouldn't need to put an additional device in the vehicle. So the goal was to create a third-party software package that could simply integrate the sign recognition capability. We've done a lot of work in AutoWare platform that is widely used by the automakers to build autonomous vehicles. Karma is the US DOT's program is heavily using AutoWare platform. We also done a lot of work in integrating our applications to Karma. We initially planned a Karma demonstration, but due to the strict timeline, we couldn't actually make it ready. But we'll be coming back to DC to do fully automated demonstrations, hopefully with the help of these signs. Here, I want to show a very quick demonstration of the system.
Can you clarify, are you developing multiple different product lines, or are all of these required to work together?
Yes, they are all working together for drivers who own a legacy vehicle. We decided to make an aftermarket product as a very affordable product. But during our commercialization studies and research, we also changed a little bit the target market. Initially, we are targeting fleet customers who would like to collect data from their roads, infrastructure, or so many different purposes. One of the very special thing about our device, it is extremely efficient. It is able to run 5 different AI models in real time simultaneously. And these are accurate models, and the chipset that is being used is very affordable chipset.
But this is all on a visible camera input?
Yes.
Okay, so you got 2 different systems going on, right? Visible camera and then IR camera with your time.
Yes, we reinforced the existing device with an not IR camera, UV camera. The IR camera would be in our research, we identified it would be slower and more expensive to acquire the sensor.
Did you use reinforcement learning? Did you have training data sets?
Well, we've done a lot of reinforcement learning for other things. For example, we have ongoing autonomous vehicle research. So reinforcement learning is very powerful in predicting the doing the path planning. So we heavily use for planning the vehicle's path using, and also deep reinforcement learning can be is a way to teach our AI model from a computer simulation, and we don't have to collect a lot of real world data. For this application, we were able to collect quite a bit data. So we didn't really need to use other tools to generate the similar data in a simulation environment. But in our future goals, we have different ideas to integrate. So I want to show you very quickly this.
I just told Ejin,
Mhm.
if you want, she can share her
All right.
the YouTube.
Mhm. That would be perfect. AJ, if you're able to hear, would you play this YouTube video here?
Whereas you talked about the device itself, so how much will a sign cost?
So for this sign, it's not a special material. So you can use a sign vendor the signs that we brought here. We paid $100 for the highest quality aluminum sign.
Showing, but it's not showing that. She's showing to the participants.
Okay. So the participants should be able to see, but I can.
You prefer we hold the questions because I know there's 20 people on the Zoom.
Oh, okay.
If you could explain about the video that you're showing.
If I can, I guess, close my sharing, then it
Yeah,
would
the
solve.
you're
Okay.
sharing, you're sharing this close, but it's not,
Yeah.
just the screen is not matching. If you can move this.
All right. Yeah. All right.
Maybe she can.
AJ, would you start from the beginning again, the video? All right, so here we place one of our smart signs. This is an automated vehicle demonstration we did to Orange County in Florida. Here, there is a work zone, and we learned the road geometry information with the help of the sign. So here, we are not using a lane detection model or anything. And in these configurations, lane lines are not visible a lot of the times. And there's a very challenging detour here. And our vehicle was able to navigate here very easily since we already projected the information coming from the road geometry data. We also added a lot of data collection here. So it collects data about the signage in the work zone, real-time position and heading of the workers in the area, and records this data for agencies to use.
So for the vehicle that you were using here was an autonomous vehicle?
Yes, we semi-automated driving. So we also have a bigger brother of the device we made. We added a depth sensor that is able to do level 2 automation. For our commercialization goals, we decided to go with non-automated low-cost device since there's quite a bit legal challenges selling an automated driving product to the consumer or other customers.
So are you able to say who the autonomous vehicle belongs to?
So we, for fully autonomous driving, we collaborate with the University of South Florida. They have 2 fully equipped vehicles that is capable of doing level 4 autonomy. But our device will be able to do lane keeping and following a route, identifying the roadway objects. It's simply level 1 to level 2 automation. But this as I'm going to show you during the demonstration, we have different versions of the product. This product has more sensors on it that allows us to do also this automation.
Not this particular demonstration.
Yes.
Which vehicle was that?
This is our vehicle that we changed a lease vehicle to semi-automated driving.
So were you actually closing the loop around your perception system? Or
Yes,
were you
we
letting
actually
it-
done quite a bit human driving on that route just to make sure this predetermined route is gonna be working. So this is actually a predetermined route that the system learns with the help of the sign. but since the system, it wasn't equipped with a lot of sensors, there wasn't a lot of redundancy. So we were always sitting on the driver and making sure it's not doing something wrong. So it wasn't really easy to actually this much to do a work zone driving. But if you have enough sensors, this is a very feasible way to teach the vehicle how to navigate in a complicated work zone. Because as I mentioned, there's no lane line available, and a flagger maybe routing the traffic. And these are very rare situations for the AI systems. And a lot of the times they may fail to identify the flagger's action or how the lane geometry is occurring in the area. So in these scenarios, these vehicles have to get some information outside. So that's why connected vehicles are very important. They need additional information from the infrastructure. In this scenario, we are simply using a smart sign instead of using a wireless communication.
Do we have more on the presentation?
Very quickly.
Change the screens again.
So for the demonstration, just to be clear, was it running in parallel with the semi-automated driving system? So that you were letting that system run, but you were recording and training your Vision Connect Plus, or your Vision Connect Plus was actually outputting data that determined how the semi-automated driving system is operating?
So we determine the route that the automated driving system should follow for the detour, but the system learned that information because the localization is the biggest challenge. The vehicle needs to know exactly where it is located in reference to this data that we are giving them. So these signs can help the vehicle calibrate this position and heading, because there's a visual identifier on the scene, and while the vehicle passes this sign, it calculates its relative distance and angle to this smart sign, and the smart sign's exact position is known since we did surveying at that point to prepare the message data. So the vehicle can now localize itself a lot easily, and now that we solved the localization, we can simply give the predetermined route to the vehicle to follow it.
If you would please continue the presentation, so after that we open the floor for people that are joining virtually for the question. If you could share what we have, it's not shared.
Oh, it's not shared? Okay.
Not share screen.
Screen.
Yes, thank you.
So we done a lot of prototyping work. We collaborated with a prototyping and manufacturing assistance company. They were also located in the same research park facility. So it was so easy to work with them. We've done a lot of different versions. So it's an iterative process. From the initial design stage, we done quite a bit changes. So this is actually one of the early ones that has a depth camera, another camera for data collection. So this version can do some automation, but we also later made the a most affordable version of the product that solely focus on the driver safety rather than the automation. So this is the latest product we worked at. It has an embedded screen, a graphical interface that animates the detected roadway users, and on all the safety warnings that we design. Simply, all the ADAS and I2V messages and the safety warnings are kind of animated in the environment. We try to minimize the driver distraction by finding the optimal position of this device on the windshield. So we've done a little bit of research on that too. We've done a lot of academic work as well, presented at so many conferences. We publish journal articles with Dr. Bani Hashemi and James Paul, and especially we were very active at the TRB and published 3 papers at the Transportation Research Record. As I mentioned, we've done quite a bit of presentations at the ITS World Congress, TRB meetings. We got different patents for different portion of the work. And recently, this collaboration with the University of South Florida that led us to win this major award from the Department of Energy. In this work, we are actually targeting some continuation of this machine vision communication idea. We are going to be testing flashing sequences of headlights and taillights to send messages to the infrastructure. We have a dynamic signs that is changing the message versus using our static signs here. So we had a multifaceted market. We decided to focus on first doing some pilot projects just to prove the technology's feasibility, collect data, and also measure how much safety benefit we can actually bring to these counties and cities. So these are some of the agencies we've been working closely. I didn't mention Sumter County here, but in our pilot projects, we do a 2-phase pilot. In the phase 1 pilot, we only put these devices in the counties or cities' fleet vehicles. They determine 5 different locations for us. Those are safety critical locations that they want to improve the traffic safety. We do a 3-month data collection just to make sure the system is reliably working, and they get familiar about this more technology before we do a more real world pilot. In the phase 2, we simply distribute these devices to volunteer residents and get more realistic data. These devices, aside from the V2I capability, it is equipped with so many different driver safety features. So we decided to target also fleet customers just to improve their fleet safety, but at the same time, give them a lot of data collection capability. So a roadway agency can collect data about the pavement condition of their roads or retroreflectivity degradation on their traffic signs. So many different applications can be implemented by just tweaking the AI models for different goals and purposes. We didn't want to target consumer market, but our idea was we talked to a lot of dashcam manufacturers. They're interested in doing new generation dashcams that can collect data, process them at the edge, rather than sending footages of gigabytes to a cloud system. It would violate a lot of user data privacy to share this data to the cloud. So if they could process this data on the device itself, they could do a lot of different applications. So our unique commercialization idea was to offer them a very efficient software that can be simply integrated the dash cams with very minor reinforcement in their hardware. we use these accelerator chipsets that we created the concept and design that will simply boost their AI capabilities of these small devices. There are also other companies who were testing in the past, implementing or testing different similar ideas of using smart signs. 3M was one of the companies who has done some work in the past. Their goal was, their approach was quite different than ours. So they were very much interested in, seeing what we are going to do and how the technology proceeds. Talking to automakers was, of course, essential, but they are the most resistant in this market space. So I'm sharing all these market strategies because SBIR also heavily focuses on commercialization. So to be able to this SBIR funding, if it is able to reach to market and successful commercialization, it's going to reach the main goal. So we spent a lot of time to find the niche market strategies. So these are the phase 1 and phase 2 testing and deployment that I mentioned. We done a lot of different sharp curves, intersectional situations, pedestrian school zone crossings, and work zones. They were ideal case scenarios for these applications. So this was a phase 1 pilot in Sumter County, Florida, but we'll be demonstrating something very similar today, and it will be live broadcast to the audience on the Zoom call. We met with a lot of different cities and counties, done a lot of conference exhibitions, technology demonstrations at different events. So these are the other application scenarios we have investigated. One of the interesting things is traffic sign adversaries. This is a growing concern. With small modifications on the traffic signs, we learned that a lot of the traffic sign recognition systems on the market can be easily tricked. So here there's a Tesla being tricked into recognizing a stop sign as a 80 speed limit sign. So instead of stopping, it's actually accelerating to really high speed. The process is simply you reverse train the commonly used AI models and try to find these sweet spots that will change the classification scores. Our solution could help solving this problem. So these invisible films can be actually a security patch on the sign, just like the security patch on security system in a banknote. The camera system can verify this information that the AI system is classifying. So if there's a mismatch of information, it will deactivate the adaptive cruise control or simply stop the vehicle to let the vehicle make a safe stop in a traffic adversary situation. This was a NASA SBIR phase 1 white paper. We're still expecting some the result of our proposal, but the idea was to use this idea of smart signs in a way that we could have autonomous navigation of space rovers. So Mars has a very rough terrain, and there is no wireless communication can be very tricky. There's high electromagnetic interference in Mars. Emission vision communication could help these autonomous rovers map the terrain of Mars surface, so they can navigate much easily. So this was another interesting idea. I mentioned the new award from the Department of Energy. They're using different ways of using mission vision communication from, as I mentioned, headlight, tail light flashing sequences to dynamic signboards, and also edge nodes on the system that can talk to Karma Cloud or integrate to other systems. Thank you very much. I hope you enjoyed the presentation. I'm really excited to show actually our demonstration. So we are going to take 15 minutes break to set up the car for the demo.
Before that, open the floor for
Yeah.
whoever is connecting to us.
Yeah.
If you have any question, please raise your hands. I would call your name and you can ask your question.
Maybe we can switch the screen.
Everybody connecting
Yeah, sounds good. Stop.
virtually has any question? We're not, inside the room, we have some questions. Please go ahead.
So when you go back to the application side, you mentioned like a lot of applications, lane departure warning.
Mhm.
So the only application you guys have developed is the static sensor, right? TSR.
No, we done also for collision warning, lane departure warning to and intersection violation warning. In that scenario, this system calculates the distance to the traffic light in real time and calculates the side stopping distance and determines if the vehicle will violate the red light. The goal is to alert the driver before making that happen. We have others, our team was very experienced in transportation research. So we were able to design some unique safety scenarios where you wouldn't be able to find in the market comparable products. So we've done a lot of dilemma zone work too that we are still in progress to integrate. And also some intersection collision applications and unsignalized intersections. So if there's a vehicle available at the intersection while our driver is approaching to that intersection, we'll try to alert the driver accordingly. Or if there's a fork merging, so the vehicle will track the other vehicle traveling on that fork and alert the driver accordingly. So we don't want to overwhelm the driver with a lot of alerts. Now our work is trying to optimize that. In this demonstration, since it's a demonstration and testing unit, we'll try to show as much information as possible. So there will be a lot more alerts than you would expect in a product. But thank you, it was a good question.
Any other questions from the room? Okay, the plan is until the team prepares for demo, maybe about 10-15 minutes. There will be a break for whoever connecting virtually. We're gonna broadcast one round of the demos, and then the broadcast ends. And then whoever is present here and they want to participate directly in another demos, they can do that.
So you won't have to leave the meeting. On the same meeting, we'll be able to join from our vehicle to Zoom call and share the broadcast data.
Yes, thank you.
One last question.
Of course, there's many questions.
You didn't raise your hand.
Yeah. Do you use GPS, or is your proposal to supplant GPS potentially? Let's say if you're in a GPS denied environment.
So one of the interesting things we discovered, we were demonstrating in Florida Automated Vehicle Summit in Miami. So our GPS on our phones were failing all the time because of the high-rise buildings. So we couldn't even go back to our hotel. So in that scenarios, our signs could help the vehicle navigate without relying on GPS, because it's simply helping the vehicle to localize in reference to road geometry. So by just using machine vision, we can navigate the driver to a limited route until the vehicle goes online with the GPS data. So that's something we are currently trying to improve.
So that's because the coordinate of the sign is already known by the
Mhm.
system.
Exactly. So the coordinate is known. We can track still this. The sensor is called IMU. After passing the sign, we can still to a distance estimate our position in that data using this IMU sensor. It's a very low cost sensor that is already coming with the depth cameras. And we are able to use geofencing in the matching of these sign messages, since there are only limited number of combinations that we can create these unique images. We simply decided to add another level of redundancy by simply geofencing the number of combinations that can happen in the area. So in simply the vehicle searches the sign match in 2-mile vicinity versus trying to find the best match with millions of signs.
Thank you.
All right.
Let me see if I have access to your calendar. Oh, you're still trying to figure out what's on your calendar.